Hi, this is Ms. Fitzmaurice, and this video is an explanation of the free response problem on page 18 of your Unit 4 packet. Alright, so again, what I want you to do is make sure you try this problem first. Give it 10 minutes, go through A, B, C, D, write down what you think you need to do, and then just get as much as you really can done in 10 minutes. And then watch this video. Okay, so again, we're going to start with what you need to do for each part. It says, a 70-kilogram woman and her 35-kilogram son are standing at rest on an ice rink as shown above. They push against each other for a time of 0.6 seconds. Okay, so on the side, maybe I'm just making a list of, we have M1, we have M2, we have a time, and they glide apart. So we know the speed of the woman immediately, so maybe the mom. So we have V1, the final speed, and we want V2, the speed of the son. Okay, so in part A, at the beginning we know that V1 naught equals V2 equals 0 because they were standing there. We have all our M's and V's, and momentum is conserved. There's two objects acting on each other, so in part A we're going to use conservation of momentum. In part B, it asks us to calculate the magnitude of the average force during the time they push. Okay, and so we know a bunch of stuff about momentum. We want to know force, and that should immediately call to mind F average times delta T is equal to M delta V. Okay, so in B we're using this impulse equation to calculate F average. In part C it says, how do the magnitude and direction of the average force on the mother by the son during the push compare with those on the son by the mother? Okay, it's talking about forces from one object on another. That should automatically make you think of Newton's third law. Okay, that they should be equal and opposite. And then D asks you, after the initial push, the friction that the ice exerts cannot be considered negligible, and the mother comes to rest after moving 7 meters. Okay, so it asks, if their coefficients are the same, how far does the son move? Okay, so if we're considering friction, when in doubt, I'm just making a figure, but you're drawing a force body diagram, you're probably going to use Newton's second law. However, we want to know about distance, okay? And we don't know time, but probably from this we can calculate acceleration. And we already know initial velocity, so that should tell you you're going to end up using the second equation, v squared equals v naught squared plus 2a delta x, because when someone comes to a stop, their final velocity is 0. Okay, so if you weren't able to complete the problem before, what I want you to do now is I want you to go through and use these steps to make sure you solve the problem. Okay, once you've done that, continue watching the video to comment on your solutions. Were you right? Were you wrong? Were you half right? What do you need to ask me when we get back to class together? Alright, so part A, we want to know the initial speed of the son after the push. So we're using conservation of momentum. We know at the very beginning they were just standing together, So their total momentum at the beginning had to be 0. And then afterwards, we can go ahead and plug in the mass of the mother times velocity of the mother plus mass of the child times velocity of the child. Okay, and that all has to be equal to 0. Now the way I've drawn it, the mom is moving to the left. Alright, so we know that the mass of the mother is 70 kilograms. And the way I've drawn her, it looks like she's moving to the left. And so I'm going to say her velocity directly after they push off is equal to negative 0.55 meters per second. Okay, and then the mass of the child we know is 35 kilograms. We don't know the child's final velocity. Okay, so we can pretty easily solve for VC. I'm going to spare you the algebraic details, but when we go ahead and solve, we find that VC is equal to 1.1 meters per second. Alright, so in B, we want to calculate the magnitude of the average force exerted by the sun, on the sun by the mother during the push. So F average times delta T equals M delta V. Okay, and it's the force on the sun, so we care about the sun's change in momentum and the sun's mass. Okay, so we know the sun has a mass of 35 kilograms and that the sun's final velocity is 1.1. The initial velocity was 0. Okay, we also know from the problem statement that the change in time was 0.6 seconds. Alright, so when we go ahead and we do that calculation, we find that the average force was equal to 64.2 newtons. Okay, part C, it's asking how the force on the mother should compare to the force on the sun. Okay, now because they are a Newton's pair force, we know from Newton's third law, says that we should have equal and opposite forces. So F average exerted on the mother will be equal, so 64.2 newtons, but in the opposite direction, so I have put a negative sign right here. Alright, so D is the tricky part. It says after the initial push, the friction that the ice exerts cannot be considered negligible, and the mother comes to rest after moving a distance of 7 meters across the ice. Okay, so what we can do is we can first find acceleration of the mother. Okay, to do this we can use our second equation. So we have, and this is all about the mother. Remember, we're sort of doing calculations for the mother, and then we're going to do calculations for the child. Okay, so we have v squared equals v naught squared plus 2a delta x. Okay, we know that delta x is 7 meters, so we have 2 times a times 7. We know that the final velocity of the mother is 0 because she's coming to rest, and the initial velocity is her 0.55 squared. Okay, so when I go ahead and solve for acceleration, I end up with 0.021 meters per second squared. Okay, this is a pretty low acceleration, but that's okay. I'm going to use this acceleration now to find mu. Okay, because I know that the coefficients are both the same for the mother and the child. Okay, so to do that, I have to draw a force body diagram of the mother. I have, of course, Fn and Fg, and then friction is acting opposite of the direction she's moving, so I have, in the x direction, when I have sigma Fx equals max, I see that Ff is equal to her mass times her acceleration in the x direction. Okay, I can write out sigma Fy equals may, and I have Fn minus Fg equals 0 because she is not moving up and down, and I find that the normal force is equal to Fg. In her case, it's mg, so that will be 700 newtons in her case. Okay, of course I know that Ff is mu times Fn, so I have mu times 700 is equal to her mass, which is 70, times 0.021. Okay, I divide both sides by 700, and I end up with mu is equal to 0.0021. Okay, and I'm going to take this and I'm going to apply it to the child. So I'm going to the next page, but keep this number in mind. So eventually I want to know how far the child gets before coming to a stop. So I'm looking at this delta x, and eventually I want to use this second equation. Before I do that, I have to calculate acceleration. I already have v initial, which is 1.1, what I solved for in A, and v final, which is 0. Okay, so I need to first calculate A, and to do that I need to draw a force body diagram of our child. Okay, so I have the same force body diagram of the mother, of course, just different numbers, friction, going in the opposite direction of movement. And so in the child's case, I have sigma Fx equals max, and sigma Fy equals may. Okay, hopefully you can see at this point that Fn of the child will be equal to Fg, or mg of the child, and that in the x direction I have negative mu times Fn is equal to max. So I have minus mu mg equals max. I can cancel out the m's, and I'm going to solve for g. I'm going to do it down here. I have ax is equal to minus mu g. Ax is equal to minus point, which is actually equal to negative 0.021 meters per second squared. Okay, now we can put this in for A, and we have 0 equals 1.1 squared plus 2 times negative 0.021 delta x. And we can solve for delta x pretty easily, and we find that the child ends up going about 29 meters. Alright, so I hope this has been helpful, and I will see you on Tuesday.